Yeah. Oh, nice.
But I mean, like, okay, everybody. All right, I think. Hold on, just let me check. Make sure we got audio. We do. Okay, so the Wi-Fi wasn't working, so I had to connect it directly to the stream. So I wanted to go over mainly talk about batteries today, but also just the last little finishing questions people have. So most of you are well on your way debugging your boards, and there's lots of sort of hacking together and jumpering, and that's fine. That's all part of the process. But for, some of you, when if you're having an issue with your board, unfortunately, there's all sorts of things that can go wrong. You flip a resistor value while you're assembling, anything like that. The one thing I've recommended to people is, put like a 100 ohm resistor between the terminals of the power supply, adjust the power supply voltage, clip it as if it's a battery. So make the power supply a virtual battery, but you can't just connect it directly. You have to have a resistor that allows more than 10 milliamps to flow. That lets you just program the voltage up and down to simulate the presence of a battery. If you start to have an issue or if you notice something wrong, really there's no better way to debug the circuit than to just start measuring, use a multimeter and start measuring your voltages around your circuit from the left side to the right side until you see something that's not what you expect. So start going along, noticing everything's okay until you notice something that's amiss, and that'll help you debug the issue. So I'd say more than half of you have had some kind of an issue with your board. Unfortunately, there can be a lot of weird things, right? There could be a resistor that looks like it's soldered, but it's not quite soldered. A lot of people have had that. There can be a resistor where people thought that it was like a kilo ohm and it was 100 kilo ohms or something like that. So all kinds of weird issues can happen. If you added test points, it'll really help the process of testing. But if not, just pick a side of a resistor. That's a lot of times the best. Other thing to note, though, if you had a lot of flux residue, especially if you did reflow with the paste. If you did reflow with the paste is it's what's called a no clean solder paste. And that's deceptive because no clean means it doesn't have to go through a cleaning process. But normally what no clean means is the flux forms like a shell around the solder after it's finished melting. And that can be hard to get the tip of a probe through sometimes. So sometimes even if you touch the probe to the shiny metal thing on the side of a resistor, sometimes you gotta get a little scratch. If you used solder paste and did a reflow with it. Or you can always just wash the whole thing with alcohol and it gets that little cocoon off the outer edge, and that works too. But that's one thing. A lot of times students will be measuring, if they don't have a test point, they're trying to measure the side of a resistor and they'll get a wonky value and it's just they're not making a connection because they haven't broken through that little crust. It's like it's a transparent crust, which is a problem. But again, that's if you're just using normal solder and normal flux, the normal flux is sticky and the probe tip will break right through it. The other stuff, not so much. So I want to give you, when I talk about batteries today, the battery video that we have added is because of it's become a big issue with student projects, become a really important need for student projects. One thing that I want to stress though is when calculating energy. So today we're going to talk about batteries and calculating energy, and there's going to be a pitfall that I talk about, which is how students calculate energy, and I'm going to use kind of like your project as an example. So, in your project, you have, for most of you, you have an op amp or something that is driving like 10 milliamps to a battery. And so a lot of times people will say, we have 10 milliamps flowing through the battery, and if they're doing a power calculation, they could just say, okay, let's estimate 3.7 volts here. And they would say, all right, 3.7 volts and 10 milliamps, that's going to be power is equal to 3.7 times 0.01. So let's say, okay, my power to this battery is 0.037 watts. And that's true in terms of the power to this battery. But that's not necessarily true in terms of the power consumed by the circuit. So one thing about an op amp is, we can use op amps to generate a voltage across some load. Right, let's say we have a resistor here, it's like a 1K resistor. And let's say we configure this op amp to output 2 volts here. So once again, you have a very easy issue. You can determine the power delivered to this resistor, and you could say power is equal to V squared over R. That's going to be 4 divided by 1,000. It's going to be whatever. And that's all well and good, but the question is, how is this op amp generating this 2 volts? Well, internally in this op amp, ultimately there's ultimately at the final stage of this, the 2 volts is being generated by these gates in here. So let's say your op amp is powered by 10 volts here, negative 10 volts here, and you're generating 2 volts across this resistor. Well, so what's actually happening is internally, this op amp is controlling the gate of this transistor such that there's an 8-volt drop across this transistor. And that's how it's maintaining 2 volts at its output. But when it comes to power, what's happening is you actually are burning this full 10 volts. So this current flow through the resistor is flowing internally through the op amp, out through the load. So it means internally in this op amp, you're burning 4 times as much power as you are at the resistor. And so when it comes to like power calculations for things like op amps, it's tempting a lot of times to just estimate power based on the power to the load. But notice with something like this, in order to deliver that controlled voltage to the load, you're burning a lot of power internally. This is very analogous to a linear regulator. So with things like op amps, when it comes to power calculations and power consumption, all that matters is the current that's consumed. Because ultimately, all the current that flows through an op amp is flowing through the rails. So even if you're only outputting 2 volts, you are still losing that full 10 volts of power being dissipated. And again, linear regulators work the same way. Linear regulator, basically you have some input output, and you are controlling this gate of this transistor. So let's say your output, let's say you were regulating to 3.3 volts, and your input was 6 volts. You are controlling the gate of this transistor such that you're going to drop 2.7 volts across the transistor. And that's just burned. You're just burning all this transistor is doing is it is just dissipating power in order to drop the voltage. It's dissipating energy to drop the voltage to produce that output. So when it comes to the power consumed by a circuit that's driven by a linear regulator, it's all just a matter of what was the input voltage and what's the current consumption. And some of the power is going to be dissipated by the linear regulator, some of it's going to be dissipated by the load. But the same is not true with switching regulators, with buck and boost regulators. Buck and boost regulators, they are able to actually change the voltage while preserving energy. So they're able to take an input voltage, store energy from that input in an inductor in a form of magnetic flux, and then use that accumulated magnetic flux, and then use that accumulated energy to deliver it to the output at a different voltage. So when it comes to switching regulators, the energy is a matter of, ideally, it's perfectly efficient, the power transition, but in reality, there's going to be some inefficiency. So let's do a theoretical problem on something similar to your op amp design. So you have an op amp. Okay. let's say your circuit boosts. Let's switch. Trying to get a little sketchy here. I'm going to switch back to YouTube too so I can see. Oops. We got 4 people watching. So your circuit is going to boost 3.7 volts to 10 volts, just for a hypothetical. And it's going to do so with 90% efficiency. Did I spell efficiency wrong? Doesn't matter. Near the end. Efficiency, I don't like that word. It feels wrong. Okay. And then this 10 volts getting off the screen for the. Oh, yeah. Out of me. Maybe people can still see that. I'm not quite sure. So you're taking a 3.7 volt input, you're boosting it to 10 volts. Then that 10 volts is powering an op amp that's providing 10 milliamps to a 4.2 volt load. Assume everything else is totally efficient. So assume that the op amp doesn't internally burn any power to run its internal control circuits. That's not a good assumption normally. Normally op amps take between 3 milliamps and about, good op amps will only take a few microamps to power their internal control circuitry. But the LM358s, I think they're about 1 or 2 milliamps of internal. Sometimes that's called quiescent current. I literally I learned how it's pronounced and then I always forget immediately. QI. But so assume this is totally efficient. Assume it's totally efficient and assume that your battery is 250 milliamp hours. My question is, how long will your battery last? We have to do broken sentences now because we're near the end of the course. Now, when I say total efficiency, though, that does not apply to the sort of general behavior of the op amp. So what we just talked about with the op amp, where it doesn't matter if the op amp is producing 4.2 volts at its output. All that matters is the current and the voltage that you're powering the op amp with. So based on this information here, I want people to you can break up into groups or whatever, take a stab at solving this question of how long is this battery going to last? And then we're going to come back together and we're going to sort of do it again. Or we're going to walk through it. This is very important for one of the questions on the final too. So I'm picking this to be an illustrative example of sort of the types of challenges you'll encounter when estimating power. Okay, break. The end of the quarter, you got to meet somebody new.
I don't think it's not quite.
Yeah. But I mean, like, you know, like five.
I mean,
Really interesting. Maybe NASA. Yeah. Oh, that could
between what's not and what's not.
Okay, how's that? However everybody's doing. Okay. So what did you come up with for, what was your approach? Anybody want to volunteer their approach? How they started this? I guess first of all, you started this end or you started that end? How many people started here? How many people started over here? Oh, okay, all right. So I'm curious, people who started here, what was your approach? Yeah.
Yeah, so my approach was, so that's like a 6.3 volt like difference. So I have to account for that somewhere. So 6.3 volts is being, I guess, added to this voltage. So it'd be like, instead of it being sucked up, for instance, it's being added. So there needs to be some type of power consumption there, I guess. There's also a 4.2 volt load. So there's like 2.1 volts not accounted for. I'm not sure if that's a remotely right direction, but I was trying to figure out what voltages are accounted for where in the circuit.
Right. So yeah. So the increase in voltage here. This is a boost converter. Saying is 90% efficient.
Yeah.
So what the boost converter does is it takes a high current and low voltage and converts it to a high voltage low current. And so ideally those would be equal. VI equals VI. In this case, it's 90% efficiency. So one thing that some people do though is knowing that there's this, as the voltage goes up, the current goes down. Some people start with the current side of things, right? They say basically, okay, like, 3 milliamps of current in this universe is 10 milliamps of current in this universe. So that's one way that if people do start from this side, that's one way to do it. What about people who start from this side? What did you do? Yeah.
I kind of found the power by doing, the 10 volt that we're supplying off with, and then multiplying it by the current. And then to find out like the power on the input side, I just did 1.1 times that power was on this side. On the output side.
Yeah. Okay. Right. Yeah. And that's. Did anybody do it who started on this side do it differently than that? So the thing was, it was calculate power on this side, and then scale the power due to the inefficiency, and then move on from there. Anybody do it differently who started at the other end? That's probably what I would do. Yeah. So yeah. One of the biggest things here is noting that your op-amp's powered by 10 volts, and it's providing 10 milliamps. So the power consumption at this end is going to be 10 volts times 0.01. That's going to be 0.1 watts. And this is definitely where people get tripped up the most, is they don't realize that when it comes to an op-amp produces its output voltage by burning voltage across the internal transistor. Yeah.
So then do you have to take that 0.1 watt and then divide that by something?
Yeah, so I always second guess myself. So you said like multiply by 1.1.
I did, well then my calculator I did times
1 over
0.9, 1 over. So
Yeah.
It worked out.
I always second guess myself. So whenever there's an efficiency, I always say like P in, or sorry, P out equals 0.9 times P in. So then I would say, okay, the output power is 0.1 watts. So the input power, 0.1 divided by 0.9. One over 9. So now we have another question. Another question is, okay, so one of the nice things here is we're already in units of power. So we already know the power in. So we don't have to mess around with voltage and current anymore. Not necessarily, right? So ultimately, you're going to have to get through the battery. But so the question now is basically, reduced to how long will a 250 milliamp hour battery that's 3.7 volts, how long will that last outputting 0.1 watts of power, 0.11 watts of power? So how did people tackle that? How do people go about tackling that? Anybody? People are like, it's late, it's 2 orders of magnitude late. It's late in the day and late in the quarter. And then late in the season, it's dark out there already. Well, there's a couple ways to think about the power for a battery, and this is partially, if people haven't looked at the video, I'm trying to stress that people look at the video to do the final exam. So a 250 milliamp hour battery, what that means is that this battery can provide, at its supplied voltage, it can provide 250 milliamps for 1 hour. Or it can provide, 1 milliamp for 250 hours, right? It's kind of any way you can think about it. But the rating for a battery is given in current and time. And so if you want power, you have to note that the battery also has a cell voltage. This is very important. So one of the things that people see, like I've noticed when people buy like power tools, like especially battery power tools, if you get like a 12 volt tool system versus a 24 volt tool system, the batteries will say, oh, it's a 3 amp hour battery, right? So like you'll buy a 3 amp hour battery for a 12 volt screwdriver, and you'll notice, well, the other 3 amp hour batteries are way cheaper than this other company's 3 amp hour batteries, because the other companies are like, the other companies are 24 volts. So a 3 amp hour battery is not the same amount of stored energy. It's going to depend on the actual output voltage of the battery. Another really interesting thing where you'll encounter this is if any of you ever bought like power packs to like recharge your phone, and it'll say, oh, it's a 10,000 milliamp hour power pack. But internally it's a 3.7 volt battery, and externally it's outputting 5 volts, right? So somehow in there it's boosting it. So if you ever want to know what that 10,000 milliamp hours refers to, is it referring to it can output 10,000 milliamps at 5 volts for an hour? Or is it saying it's internally it's got a 3.7 volt battery, this 10,000 milliamp hours? The key to understand it is whichever one would give a better looking appearance when you're trying to sell something, that's the one you choose. It's like if you're buying a hard drive and you're trying to decide, well, when this hard drive says it's 10 terabytes, does that mean it's 10 times 10 to the 4th bytes, or does that mean it's 10 times 2 to the power of whatever, right? So are they saying a kilobyte is 124 bytes, or are they saying it's 1,000 bytes? It's always whichever makes a better number to sell the product. So it's always going to be err in that favor. So if you buy a 10,000 milliamp hour, power pack, that's saying that internally there's a 3.7 volt battery that can provide 10,000 milliamps for 1 hour. Which means you cannot provide 10,000 milliamps to your output 5 volts for 1 hour. It's going to be scaled, right? But that's the way they rate those things. And it's, from a consumer perspective, it's very confusing, especially that case where they're giving you the rating for an internal battery which has nothing to do with the input or output voltage of the device you're buying, right? It's you're inputting 5 volts to charge it, or whatever if you're using the more advanced USB. And then it's charging some internal battery, and you don't know what the cell voltage of it is technically, and then it's outputting 5 volts. So it's charging it, and then it's boosting it to provide power to the output. Did you know the internal voltage of the cell? No. Should they have provided that? Probably. Is milliamp hour ratings useful for a device like that? Not really. But it's consistent, right? As long as they're consistent between brands and stuff, then it's okay. Same with hard drives, I suppose. But for here, this question of, so we have 200 milliamp hours. So there's a couple ways we could tackle that. Probably what I would probably do, just to make it simple, is I would convert milliamp hours to watt hours. So I would say 0.25 amp hours times 3.7 volts equals 0.25. This is where it's really important to keep your units. I think units, a lot of times units, students start to drop them throughout their education. You got to bring them back for this stuff, right? It really helps you avoid mistakes. Amps times volts is going to be watts, so we get 0.925 watt hours. This is closer to the way we actually measure power. If you buy power from a power company, they're going to sell it to you in kilowatt hours. And I don't know how much it costs. I think it's about 7 cents a kilowatt hour around here. It's a little weird. The economies of power are a little strange in Washington State. That's why they mine Bitcoin and like Twist. In the middle of nowhere, they like to set up shipping containers and mine Bitcoin to get cheap power over there. But so basically, though, it means that this thing can provide 0.925 watts for an hour, or or provide 1 watt for 0.925 hours, however you want to think about it. Right? So now a simple matter, and this is again where units help. If we want to know how many hours this is going to last, yeah.
Why do you multiply the 250 milliamps by 3.7 volts, not by 10 volts?
We had so in this case, the 3 point. This is referring to the battery itself. So basically, we found out how much power the battery is going to have to output. So our next question is how much energy is stored in the battery. So if we're talking about the battery itself, this 250 milliamp hour rating was for the battery itself, having nothing to do with what you boosted the battery's voltage to. So knowing that the battery was 250 milliamp hours and its cell voltage was 3.7 volts. And it's interesting, right? Because this ratio, this 3.7 to 10, the only time that really, we never did any like 10 divided by 3.7. It wasn't necessary. We found an energy, and then we knew the efficiency across this jump. So we never had to play games with voltage and current to move across the jump. As soon as we converted to energy, we just did an efficiency factor, and then we got to the other side of the gap. And you don't have to do it that way. You could calculate this. You could find the current on one side, and then you could take the 10 milliamps, and you could say, okay, 10 milliamps, if it's 90% efficient, 10 milliamps, converting the other way is going to be like, whatever, 40 milliamps on this side, and then you could say, okay, 40 milliamps, 250 milliamp hour battery, okay, 250 divided by 40. So you could do it that way. There's several ways you could have done this. But for me, the way I would probably do it is convert to power, and then do the efficiency factor, and then move back in the other direction and find out from the back. Okay, so we do go over this stuff in the video more, so we talk about this. This becomes important. There's other stuff in the videos we go over. For people's senior projects, one of the things that's happening more and more is people are using microcontrollers that make very efficient use of power. So we've had an increasing number of senior projects that say, I want to have something that lasts for a long time on a battery. That's a very difficult thing to do. So it's more difficult than you might think, but it's getting easier. It's getting easier because manufacturers who sell microcontrollers have realized, well, consumer or engineers who use our microcontroller don't want to have to spend 3 weeks reading through our data sheet to be able to just do something simple like put it to sleep and then wake it back up. So manufacturers nowadays have started including like example code, and they've started including driver utilities and stuff, so that putting a microcontroller to sleep can be as simple as, go to sleep. And then the efficiency of the microcontroller is not necessarily your limiting factor. And then your limiting factor a lot of times is what's the efficiency of your regulator. A lot of people say, oh, if I want a super efficient device that goes to sleep, I'm going to use a buck or a boost regulator because they're really efficient. But the efficiency of a buck boost regulator, practically, when your circuit is consuming a nanowatt of power, your buck boost circuit is not going to be efficient at all. But a linear regulator might be. So there's some trade-offs, right? We say linear regulators aren't as efficient as buck boost. But if you had to just out of the blue say, I've got a buck or a boost converter that needs to output 1 nanoamp, and I've got a linear regulator that needs to output 1 nanoamp, which do you think is more efficient? I would probably guess the linear regulator. Because at that point, the issue with power is going to be the power consumed by the converter itself, through the converter circuitry, through the behavior it's doing, switching and things like that. A lot of buck and boost converters nowadays can switch their frequency. When they realize that a load is only consuming a nanoamp of current, they'll say, well, instead of being a 2 megahertz switching frequency, I'm now a 100 kilohertz switching frequency. benefit of that is as it slows down its switching, it slows down those transistor transition events, it reduces its inefficiency. So there's lots of neat stuff like that. I'm just trying to let people know when you get to your senior project, it's not always going to be quite as intuitive. It's not going to be quite as obvious if you're playing with low power as it is in the stuff we've gone over in this class. So I want people to just be prepared for that, because the next time you see me will be for your senior project. Unless something goes wrong with the surgery or really right. I could get addicted to I could either get addicted to plastic surgery or to narcotics. Either way, it could go either way. Might not be back. We'll see. I just realized Hawaiian Airlines $79 one way, so be beach body ready. You might get addicted to
powerlifting. That's it.
What's that?
Just get addicted to powerlifting. You show up, you're just curling.
Just during class.
Yeah.
I feel like I'd find some cheap way. I'd get like those electrodes that like shock your muscles, right? So I'd be like sleeping like this, waking up buff. Wake up at 3 a.m., have a protein shake. Okay, does anybody have questions about the, yeah. Okay, about this. Yeah.
About it, trying to find the input current.
Okay.
And so we know that power in equals power out.
Yep.
And so we got 10 volts times the 10 milliamp has to equal 9% of 3.7 volts times the 10 amp current.
Okay.
And I just calculate that to find a current of 30 milliamps, and then you have your 2050 or 250 milliamp hour battery, and then divide that by 30 milliamps to get hours.
Yeah, seems right. Did you get the right answer?
I got 8.33.
One of us could have made a mistake. At this point, that's pretty close. If you're estimating battery life, you better not be cutting it that close, right? You know, we're making big things. Yeah. Did you do enough digits of the 0.1111?
I never got that because I didn't do the 9% of the power. I just did 90% of the voltage, and then I times that by, or I divided that by the power of the. So I have like this equation where I got 0.9 times 3.7 times I equals 10 volts times 10 milliamps. And then I just kind of.
So your power's kind of like in there, right? It's not explicitly as power, but it's current.
Yeah. So yeah, you just never solved it as an actual power. You solved the equation. Feels like that's right. I mean, that seems right to me. I don't know where one of us could have got a number flipped, but close. Okay, so a couple of things from what people. So I mean, the finals posted. You can all see it. Couple things I wanted to mention. None of the questions are really intended to be like trick questions. So like a few of you mentioned the one that there's a question that talks about ripple, and I say it's keep your ripple to under like 100 millivolts peak to peak or something like that. I don't mean that peak to peak to be tricky. I'm not trying to, especially since the function generators in 338, their term for peak to peak, they use it incorrectly actually. So if you program the magnitude of the function generators in 338 using peak to peak, it's actually just peak. So I'm not trying to play tricks there. I'm just, when I say that's the magnitude of the ripple, I just mean for you to put that as your delta V in your equation for calculating your boost converter. It wasn't a you need to divide by 2 or divide by the square root of 2 or any sort of games like that. So it's not meant to be tricky. Does anybody have any other questions about the remaining stuff to turn in or the process for the end of the year? I should be somewhat available. I mean, in lab time tomorrow, I'll be there the whole time. I do have to do, I'm an advisor for the Formula SAE team, and so we're going to do fuse testing in the morning tomorrow. So I might not be available. No, we're doing it in the afternoon, I think. I got to recheck my calendar, but either before or after the lab time, I won't necessarily be available. You're free to, all of you, just, do your assembly and stuff throughout the time. But if most of my helping people with their boards has been I'll like solder jumpers and I'll flip things for people and stuff like that. I think I don't do it fast, but I think I do it faster than other people getting frustrated with it. So, but I'm hoping that for most of you in the lab tomorrow, when you have if you're all ready to go, if you test it and it's good, you have no reason to show up. You don't have to show up tomorrow. But I'll be there the whole time with a focus on helping people answer any questions you have and get your project wrapped up. Help people debug, troubleshoot their project. But again, the basic thing is if something's not working, a couple tricks some of the best tricks are one, take a USB cable and cut it and power your thing through a USB cable through the power supply, and that way you can monitor the current flow. That's one trick you can do. Reza also has in his office a little USB thing that measures the current to the USB, which is a really cool stocking stuffer. You want to give people a little, they're like $8. And then just start probing everything until you notice something that's not what you expect.
For proofs that it works, can we just upload like a link to a video?
Yes, a link to a YouTube video works really well. The only issue I've had in the past is if you send me a link, send it also to like somebody else to make sure they can actually see it. YouTube seems to be fine, but when I've had people send me links to like OneDrive files that like I don't have permission to access it, and so that's really rough when it's like 2 days before your grades are due and everybody's off on Christmas vacation trying to like buy presents or whatever last minute, and then I'm like, hey, trying to get a hold of them to get them to send me a version of a link that actually shows up. So if you're going to send a link to a video, YouTube is great. If it's like OneDrive, make sure that the link actually works for people who aren't you.
Can the link be in the comments section of the submission? Like, there's like add comment part.
I would honestly just send me just create a document and just type the link in the document such as that. That's what'll show up when I do the speed grader on the tablet. The comments are kind of like hidden, and what I see is the file submission. So if you do that, that's probably the easiest way to do it. Yeah, Nick.
What are you looking for in that video? Because I just made it so that the lights flash and then the light goes off and it turns green.
Yeah, that's okay. For most people, right? It's like it's plugged in. Look, this light is turned on. If I see the light functionality, that's the biggest thing. If it's like okay, here it is, and it doesn't have to be a video either. You could take a photo of. Here's what it is when, oh, look, we're measuring 2.8 volts and the pre-charge light is on. And then, oh, we're measuring this and this is on. And I've also already told people, if your circuit, if there's a part of your circuit that doesn't work, like if the pre-charge light doesn't work or something, like that part of the circuit was messed up, you can still just say, oh, it works. The pre-charge doesn't work, but the overall circuit works. That counts too. I'm not going to as long as you fix the error that caused the pre-charge not to work, that's okay. You don't need to redo your circuit or do the test procedure if you have identified the one. If it works except for one feature and you correct whatever was the flaw with that, that's fine. You can just submit proof of the 70% functionality and I'll count that as proof of functioning. So, yeah.
So we don't really need to prove that this circuit can provide current.
No, yeah, that's a little too much. I probably won't see that in the video anyway. What I mostly want to see you do is just show me, as you cycle through it, that it goes from the pre-charge stage to the other stuff being wrong. I can pretty easily see it in your schematic if it's. Now I didn't see all of your schematics because it was possible for you to submit a board without ever getting the schematic checked off. But I will see the schematics this time for the final submission. Okay, everybody, I'm going to stick around here for about another half hour, and then I'm going to go home, and then again, tomorrow my only thing on my schedule is the FSAE fuse testing in your lab, which is also generally helping with projects. I got to check. DHL drove out of Seattle with them at 1:30 today, and at 2:30 we realized the office was locked and Reza put a sign up, but I don't think they drive that fast.
Yeah.
Just stick out and like down.
Unless you calculated the loading for this, unless you calculated the current flow through this, that's not going to generate the voltage you want. That's the issue.
Okay.
So this would not be a strong. Yeah, this is not an actual.
Would I have to put like a buffer here like that?
A buffer, yeah, a buffer would have fixed it, right? This one wasn't necessary.
Right.
This is how you driven. So yeah, buffer there. Yeah, that's the big thing I stress. If you're generating a voltage with a divider, that is a weak voltage, and so you
Yeah.
have to buffer it. Or if it went in the positive terminal, that would be fine. If it was like a non. But yeah, that's the issue with it. Is that not an accurate calculation for that load?
Okay.
But they're actually going to be pretty. Not going to be horrible here, but it's going to be a pretty big.
Yeah. Okay.
Um,
I think it'll still be.
So just like this is just like the regular like, inverting summing circuit like that's used. So is that like this is just because it's a voltage divider here? Like it doesn't. Okay. So yes, that doesn't work.
Probably.
Okay.
Yeah, on a normal summing amplifier, there is current drop. A normal summing amplifier only works if you have ideal voltage source input.
Okay.
So, just kind of like
I don't know what it is.
is that open loop
It
gain?
will not answer this.
Um,
Do that.
No, so a epsilon is
I called,
that's the
I called it a few places. I mean.
so well that is the forward. That is the book calls it the like it's sort of the forward gain. It's the gain through the forward,
3, 4 places.
which is
One
a
got that.
function of the open loop gain, and it's also a function of whatever, like if you have resistor dividers or you have a current to voltage conversion through a resistor, it's all that. It's whatever causes gain or loss to the signal as it moves through the op amp trigger to the output. So,
And so this is just loop gain.
Yeah, I think
so like in some configurations it is, right? Like when your input is directly determined to the op amp, then absolutely
that's probably the most
the
exciting.
only gain that signal sees going from the input to your output is the open loop gain of the op amp. But in a case like this, right, it's your input signal is, or your input current is producing a voltage by I times R, and then that, so it's basically getting, so,
Okay. I think I get this.
On the
Okay.
so then, yeah, the last column is just the product of the two. So
Yeah.
feedback path gain, forward path gain,
And
gain.
that L is this, right?
Yeah, that's it.
Okay. I thought I knew it when I was going into the midterm, but I think it's just this weird question on the final. Like, the open loop gain is analysis. And I thought that this was the open loop gain, so I was trying to calculate with that. I was like, this isn't weird, but if I just put in L equals A here, it was just like, oh, then
Right, open loop gain is it. Yeah. It's the little,
Trying to do like the
Yeah.
back
the little
back camper setup.
these little ones, right?
yeah, little, yeah.
Okay.
Which sometimes is the so,
Yeah. Okay.
sometimes it is the loop gain, or sometimes it is the forward gain.
Okay,
Yeah.
that makes more sense.
Yeah.
And so I don't know if you have time now or after you ask this question. Could you help me look at my board though? Because everything works and the charging's fine, but my LEDs are just messed up. And I've looked, I have no shorts on my MOSFET, and I've checked all the voltages, everything seems fine. These LEDs are just being really weird.
Yeah, I can. Question?
This was from the board problem. Like, so the inductor ripple current comes out to, I mean, I think I did it right, but it comes out to 42 amps and the output's only 10 amps. And that seemed like kind of wrong to me, just that the inductor ripple current would be 4 times greater than the output current. Because you specified it as 10 amps, and it's, if I did that right, I think I did. But
So what's going to happen though is when you have a boost converter, right? When you have a boost converter, the output current, yeah, it's high output voltage, low output current, low input voltage, high input. So the inductor ripple is the result of the input. So what's happening is on the input side, you have massive currents and low voltages. On the output side, you have small average currents, high voltages. Yeah.
So then, I kind of like forget, honestly, I just not the equations, I forget what the circuit was. The inductor isn't it on the right side of the switch? It's pretty much like the right input to the output, or is the inductor on the left side of the switch?
For a boost converter?
Yeah.
Yeah, for a boost converter, the inductor is,
And then do the final. So you focus.
So even though it says inductor ripple
right.
current, it's like the input ripple current.
And we don't have,
it's the,
it's online.
it's,
We don't have any.
well, it's the
Yeah,
current,
so
it's the,
like cake with.
yeah,
I know.
kind of, but it's
Back
the,
here.
it's the change in current for the inductor. It
Okay.
matters in terms of buying the right inductor, right? So that's the issue is, if you were designing the circuit, you might think, oh, it's okay if I get an inductor that has a little tiny current. That can handle a little tiny current. A little tiny current
It's just like a cheaper inductor.
is a cheaper inductor, but then you realize when you do the math, no, actually the
Okay. So that number does make sense.
it does make sense. Yep.
And it's like almost, it's all that extra, there's so much more current in this inductor than what we want at the output.
Up until
That's
then.
how we're getting the extra.
You're exactly.
Okay.
Yep. Yep.
Okay, I think you.
Yep.
I don't think it's. So I'm behind. I haven't turned it home 4 or 5. Is it worth?
I would.
Yeah,
Yeah.
yeah, cool. So I got the, and is there any flexibility? I guess this feels like a silly question to ask on the deadlines for, we have like what 5 things this weekend.
Yeah. So, yeah. If you can't get, so my biggest problem with, so you should be fine if you get it in by, if you get it in by Monday night, you get it by Monday night. You should be fine. But my biggest question is, I'm not sure if I'm going to be able to do the grading and stuff after, after the surgery. So I'm just not quite sure.
Right.
But yeah, so it's like, I mean, normally there would be flexibility all the way up till the Tuesday after finals week. I'm not quite sure that's going to be possible. So,
Yeah.
so I guess it's going to kind of be like, let me know on like Monday or so what's going, and I might have a better idea of like, because like if by Monday most people have gotten it in, I'm feeling pretty good. There's not much left. Then I probably will be okay with. I mean, it is still. I mean, they're due Tuesday. Surgery's Wednesday. I mean, a week later, and I'm not still going to be. Doctors get in trouble now if they give you narcotics for that long. They should be fine. They should be okay. I'm gonna be comfortable, but I might be grading your thing angrily.
No.
There'll be a pain. You'll feel pain too. But yeah, I would say just, but the other thing is that they try to get as much in, as much as you can.
Yeah.
So there's some things that are a lot of work for you and very easy for me to grade. Like, if the thing that you're getting caught up on is like proving the functionality of your circuit, that could wait. Like that's not going to take me much time to do. If your delay is turning in your lab notebook, that's more of a problem. Because the lab notebooks take me a long time to grade.
Right.
Lab notebooks are like 20 hours of me going through the notebook. Well, because I have to go through every lab that you did and
Right.
make sure you went through all the sections of it, and then I'm grading like composition of it. So it's like the lab notebook might be very little effort for you because you've already done most of it. But that's the one that I would prefer you get turned in earlier. That's the one. I think I'm still streaming actually. Uh-oh. What did I say?
Is Latin Book Friday or Sunday? Lab Notebook Sunday, right?